Okay, recording.
Okay, welcome to the second secure multi-part computation session. We're going to start with the first talk on soft-spoken OT, quieter OT extension from small field silent vector OLE in the minicrypt model from Lance Roy. So Lance, you can start.
I'd like to discuss soft-spoken OT, a new OT extension technique. So in a one of two OT, there are two messages, M0 and M1, chosen by a sender. The receiver picks which message, MX star, that it wants, and it must learn nothing about the other message, and the sender must not learn which message was chosen. However, I'll be focusing more on random oblivious transfer, where the messages and the choice bit are chosen by the protocol itself randomly and given as outputs instead. So that means it's just some correlated randomness that's correlated according to the rules of the OT protocol. So in OT extension, what we want to do is to take a small number of these random oblivious transfers, we call them base one of two OTs, and turn them efficiently into as many extended OTs as you want. Finally, there's also we can consider n choose one OT, like one of n OT, where you choose out of n messages. A soft-spoken OT supports this, but I will skip that for the talk. So, okay. There's also one last kind of OT. We consider all but one oblivious transfer. So for just two OTs, it just means that we are choosing the OT we don't want rather than the OT we do want, the message we don't want to receive rather than the message we do want to receive. So it makes no difference, like glass half empty or half full, pick the one you want or the one you don't, it doesn't make any difference. But that's where the general, that's what's different about soft-spoken OT is that once you go to all but one OT, you can you pick one message you don't want to receive out of n of them, and you learn all of the receiver picks one message it doesn't want to receive, and learns all of the other messages. So M0 up to Mn, excluding M delta. So we follow silent OT and using a puncturable PRF to generate efficiently all the all but one OTs. So these will be our base OTs. All right, so that's the types of things we use to base the protocol on. Then internally, what all OT extension protocols generate, they generate a correlation called subfield vector OLE. So it's built up to that, starting with just OLE. So in oblivious linear evaluation, or OLE, the sender learns some linear function, f of x equals ux plus v. So they learn the coefficients uv, and then the receiver learns the evaluation of f at a random point delta, as well as learning that point delta. So equivalently, they learn secret shares of the product u times delta. So the structure then is that you have two entries in this finite field f, they get multiplied. Then next is there's subfield OLE. So that means that W, V, and delta are in a bigger field, whereas U is still just a single bit, let's say, if that's the subfield. And so that if that's the case, that's called a subfield OLE. Or another way of looking at it, if you view the larger field as being like a row vector, then it's a single entry times the whole row vector. The product of a single entry U times the whole row vector delta is what they get secret shares of. Then there's vector OLE, which is sort of the other way around. W, V, and U become vectors, and they get multiplied by the same delta gets multiplied by all entries. And then finally, there is subfield vol, subfield vector OLE, where it can be viewed as like an outer product. Each entry in U gets multiplied in each entry of delta to get these matrices W and V, or equivalent again, they can be viewed as larger members of a larger or smaller field. So comparison, let's see how soft-spoken OT fits in the main classes of OT extensions. So the first main category is the seminal OT extension of IKMP. and the protocols that expired. So IKMP requires only a correlation robust hash function, which is metric key assumption. And it's also computationally very efficient. However, it sends 2 lambda bits for every OT you generate. And in many applications, your communication is very costly. So a costly resource. And so that may be a bottleneck. So the main alternative has been silent OT, which is a fairly recent result, that they use a learning parity of noise assumption and are able to get the communication cost down to as low as lambda times log of the number of OTs you get, roughly speaking. However, this also they also have additional capability. They can generate a bunch of OTs through silent preprocessing ahead of time, but I will be focusing just on like the overall cost without considering preprocessing. Their main drawback comes from the computation. They need to compute the syndrome for some large linear code, and that typically requires some like complicated memory access pattern and possibly like solving linear systems. Silent OT is an attempt to bridge this gap created between these two ranges of communication efficiency or computation efficiency. So it's most similar to IKMP. It uses only a correlation robust hash still, but it exposes a new communication computation trade-off. So for any parameter, this trade-off parameter k can take any integer value, and then the communication gets reduced by a factor of k. And it comes at the cost of using 2 to the k divided by 2k times as much computation in the form of generated bits from a PRG. Since PRGs can be implemented fairly efficiently using like hardware support for AES, this trade-off is often beneficial. So continuing the comparison of IKMP, here's an overview of the steps for OT extension. First of all, we have our base OTs up here. Base 1 of OTs of them, it requires lambda, or lambda's security parameter again. Base OTs. These are then just with some XORs, they can be converted into vector OLEs over F2, so a single bit vector OLEs. Next, de-randomization. You can de-randomize all of the U's of these vector OLEs to be the same. Once they're de-randomized, then you can stack them all side by side to get a subfield vector OLE. Then finally, if you go and look at the rows of the resulting correlation and hash them, you get output random OTs. And you can get as many as you want just by extending it to as many rows as you want. So the only place where there's communication cost in here, like after the initial setup, is this de-randomization step. You have to do something to reveal some. You have to reveal some information in order to make all the U's the same. The number of in each OT, there is a whole row you have to reveal. So it costs lambda bits per OT to de-randomize. Soft-spoken OT is a similar structure, but it starts instead with these all but 1 OTs, 2 to the k, or 2 to the k minus 1 of 2 to the k OTs. We have a new vector OLE, subfield vector OLE based on this all but 1 OT that generalizes the IKMP vol. And then again, we do the de-randomization and hash and so on. But the trick is that now because each of these is outputting k bits at a time, we only need lambda by k of them. And then that means we only need to de-randomize lambda by k bits of U every OT. So it reduces the communication by a factor of k. All right, let's see in more detail how these steps work. So in the way you can convert OT into a vol, you can XOR the bits, input bits, XOR the 2 messages together and choose delta to be X star. And then this is a vol, but equivalently, we'd write it in terms of the all but one, just to make it more consistent with this soft spoken. So this is equivalent. So you can see this is a vol because, well, either delta is 0, in which case x star is 1, and then w and v are equal. So it's just w is m1 is v, or their delta is 1, in which case x star is 0, and then they differ by u, they're m0, x or m1. All right, so let's plot what this computation looks like. All the variables are defined as like linear functions of the messages. Some product of, for each of the two options of the message, it's a product of some value coefficient as a function of x with that corresponding message. However, to make nice diagrams out of this, we need to make signs so that and replace addition possibly with subtraction in order to make it use real numbers like a graph is needs. So I just picked the ones that make the algebra work out, and it doesn't really matter which you pick. So you can see that u is this linear function here, and sorry, v is this linear function here, and u is always -1 times the message. Now w is also written as like a linear function, and you can see that its linear function is always 0 at delta here. So in this example, delta is 1, so it is only depends on message 0, not message 1. This is the fact that w has a root at delta is what lets the receiver compute w without knowing the message m delta. Finally, we get check that this satisfies the vol correlation by seeing that by checking to see like the difference between these two lines w and v is always -1, which is 1, which is delta, times u, which is -1 here. So that's ik and p. Now let's see how this works if we use a larger field as a soft-spoken OT. So again, these messages are like a single bit now, but now they're combined in a more complicated, they'll be combined in a more complicated way. So first of all, u, since it was just the sum over all, like, it was the same coefficient for all of them, let's take it to be the negative of the sum of the messages. So -1 the whole way. V, 0, 1, that seems like a pattern, x times mx. Delta, we need a root at x equals delta, so let's make it be x minus delta. And then finally, so in this example, delta equals 3. Then finally, we can see again that w minus v is like -3, which is the same thing as delta times u, because u is -1 and delta is 3. So this is, or you can check the algebra, but like this is like a visual proof of the vector OLE's correlation. So once we have this vector OLE, the next step is the de-randomization. So de-randomization is a well-known technique that turns some of the outputs of the correlated randomness into inputs instead. So in this case, we can use it to control u from the vol and change it to the u we want. So the sender computes correction c, that's just the difference from what it got and what it wanted, and gives it the receiver. And then the receiver multiplies it by delta in order to correct the result to make it match. So the next step in ik and p is to somehow combine all of these f2 vols into one f2 lambda vol. So we can write all of these out, these separate vol correlations out here. And we first need to de-randomize all these u vectors to be the same. So that each entry in u will only be 1 bit long. So once you do this, it will just be u1 here. Rather, these are all now the same u vector. And then you can stack them all side by side and get this outer product structure, just like we wanted for a subfield vol. Soft-spoken OT then is very similar, but since now these deltas are in a larger field, we can take a smaller number of them and stack them side by side together. So we only need lambda by k of them stacked side by side together. And again, since u is 1 bit each, that's lambda by k bits per OT. The final step is the same between the two protocols. The vol outputs are hashed to get the OT messages. So there's like two cases. Either u, which will be the output choice bit of the OT, is 0, in which case, since v and w, w equals v plus u delta, w and v will be equal. So then mx star, m0 will be m0, they'll match. Or in the other case, u will be 1. And then these two will be different. They'll be offset by delta from each other. But then w minus delta will be equal to v. And so mx star, when x star is 1, matches m1. However, there's one kind of funny thing going on here, which is that this is the sender, yet it was the one who received a single message and found out which message. So that's because in IKMP, the parties switch roles when they do OT extension. The base OT sender becomes the extension OT receiver. So I'm going to continue using sender and receiver to refer to their roles as base OTs rather than the extended OTs. All right, so that's how the semi-honest OT extension protocols work, soft-spoken IKMP. But there's also a question of malicious security. So far, these protocols are only actually secure in the semi-honest model. When the base OT sender behaves correctly, we get the correct result, which is outer. We get, if we call this like correlation here, we get the correct result that's outer product of the u's and deltas. Or you can write out with like when u is 1, that's deltas in the row, and other rows it's zeros. And there's never any like mix of like a row having some deltas and some no deltas when you're looking at like the difference between w and v. So this is what happens if OT extender behaves correctly. However, if they de-randomize the u's incorrectly, then they could get something else. In particular, they could since they can de-randomize them to be whatever they want, they could de-randomize them to be an identity matrix. So then on the diagonal of this, you get like the first row of w minus v only depends on delta 1, the second one only depends on delta 2, and so on. So with that, now the trouble is that if you do this now that you hash it and you use it for OT extension, there's only 1 bit of entropy. Like if I'm the OT extension sender, I know v, and w minus v only depends on the first row. Let's say it only depends on this 1 bit delta 1. So there's only 1 bit of entropy in what the other party has. So if I learn their messages, I can brute force just like 2 possibilities to solve for delta 1. Now I could do that independently for each row and learn their whole secret delta. And after that, I know everything I need to know to attack every subsequent OT generated by the OT extension. So to fix this, the standard technique is a consistency check. So I'll present a simplified version of soft-spoken OT's consistency check, which is similar to the OS consistency check. So the idea is that since in a consistency check, part of the correlation they have is revealed and checked, while the rest is kept secret. So the idea is that since the correlation is preserved by multiplying on the left by a matrix, multiplication by a matrix preserves the subfield vol correlation. You can reveal only a piece of the information, have it check the whole thing. To more precisely, the OT extension receiver, the base OT receiver generates a random matrix R, which they send to the sender, and the sender computes R times its inputs and sends them back. Now, if they're behaving honestly, the correlation ought to hold on R times these things, these consistency checked versions of V and U. So the receiver will abort if they do not match. And then this reveals, so if R has S rows, this reveals S rows of information about U, V, and W. So you burn the last S rows in order to preserve secrecy. So S controls how likely it is they can break the scheme. So there are several malicious OT extensions based on consistency checking, and here's a comparison of soft-spoken OT with these. So to make it apples to apples comparison, these are all as they're all displayed as like how they would be if they were instantiated for one of two OT, even though some of these papers are originally for like one of an OT. So first of all, there's the OT extension, a result of CCG. They are actually the most similar to soft-spoken OT. They just have we have a slightly tighter proof than they do that lets us give a slightly better bound here. And so you just send half the information for the consistency check. Otherwise, it's very similar. Unfortunately, we found some flaws in the previous work, however. So for OOS, the flaw was just in a proof, and the special case of the soft-spoken OT's proof applies to OOS, and so it's still secure. We found a couple of attacks on KOS. One that only violates an internal lemma and is like completely impractical. Another that's also completely impractical, but not quite as impractical, and actually attacks the protocol itself. But it only works for a weird special case where the security parameter is a multiple of 20. But finally, there's PSS. That result was more flawed. And in particular for lambda equals 128, we can break PSS with probability 1 over 256 using only 2 to the 18 hash evaluations. So we implemented soft-spoken OT in the libOT library and benchmarked it to compare with leading OT protocols. The parties are each run single-threaded, with each party on its own core of a dual-core processor. We implemented network settings of localhost, where bandwidth is unlimited, LAN, which has a 1 millisecond latency and 1 gigabit connection, and WAN with a 40 millisecond latency and 100 megabits bandwidth. The times are for generating 10 million OTs. So in each column, the first place is bolded and the second place is underlined. So in the LAN and localhost settings, soft-spoken OT is significantly better than the other protocols. However, in the WAN setting, soft-spoken OT takes second place to Silver, which is a particularly efficient version of silent OT. The overhead of these version protocols in maliciously secure setting are fairly low, as you can see. Also, there's a plot of the same data. You can see that there's on a log scale of nanoseconds per OT. So say in the LAN setting, it's a fairly significant improvement for soft-spoken OT, but in the WAN, it's a little bit worse. It's a few times worse than Silver. All right, so thank you for attending my talk on OT extension.
Thank you. If you have any questions, please come at the front, at the microphones.
Thanks for the talk. I just had a question about those graphs that you showed when you were, I think you were explaining like the de-randomization step, or maybe it was the
this is the vol.
Yeah, could you explain those graphs? The graphs showing lines again.
Sure.
Yeah, like what was going on the previous slide too?
So this is the full graph for the soft-spoken OT. So each of these lines represents the coefficient of the message. So like U, this value U is calculated as the negative of the sum of the messages. So that's -1 times each message.
I see. Okay, so that's
you can say each message goes as a position here, and then the corresponding Y coordinate is what do you multiply the message by in order to then sum and get U. And then for V, it's like you multiply each by like, this message 3 by 3 and then sum to get V and so on.
Okay. And then the difference.
So the difference V minus W is going to be the sum of the individual differences here. So the say message 2 gets multiplied. So in V, it gets multiplied by 2, and in W, it gets multiplied by -1. The difference there is going to be -3.
Okay, thank you.
And it's the same for everything, as you can see.
All right, thank you.
So there's no time for another question. Let's thank Lance again. Next, we have Rex. Rex, are you online? Can you share your screen?
Yes, I'm online. Just a second. Okay, do you see
Does-
my slides?
Yes, and it's recording. Okay. So we're moving to the next talk of the session on maliciously secure massively parallel computation for all but one corruptions from Rex Fernando, Yuval Yeles, Ilan Gomagorski, and Elaine C. And Rex is going to give the talk.
Okay.
Oh, just a second. Don't start yet. We don't see your slides on the screen.
Oh, really?
No, you don't have to do anything. It's for the room here.
I see. Okay. Just let me know when you're
Yeah.
ready.
Okay, you can start now.
Okay, sounds good. So thanks for the introduction. Like Antigone said, I'm going to be talking about how to achieve malicious security for massively parallel computations in the setting of all but one corruptions. And this is joint work with my co-authors Yuval, Ilan, and Elaine. So the topic of our work is the type of like large-scale distributed computation that happens commonly inside data centers. And so a characteristic of this computation is that the data set is very large, and this data set is distributed among many different machines, and each machine has a very limited local space in proportion to the data set. And the most, like probably the most famous example of such a distributed algorithm is the Google search algorithm. So the question that we're interested in studying is what's possible in terms of security for these types of distributed algorithms. So we work in a model which is called the massively parallel computation model, or the MPC model. And this model has been used by the algorithms community in many past papers to study the types of distributed computation that I was just talking about. And at a high level, the model works as follows. So there's a large input string, and this input string is divided among many different machines, each with a local space S that's much smaller than the input X. And these parties run a protocol, and the output of the protocol is defined to be the concatenation of the local outputs of each machine. And so the two main important constraints that the model imposes are first that the local space of each machine S is equal to n to the epsilon, where n is the input size and epsilon is some arbitrarily small constant. And a corollary of this, this constraint is that we assume that communication costs space. So this is a communication bounded model, and in particular, there's no broadcast. So the second constraint is that we're going to say a protocol is efficient in this model if it takes if the round complexity is small. So it should take logarithmic rounds or less. So the question that we want to ask in our work is whether or not it's possible to achieve security in this model akin to what classical secure computation protocols provide. So in classical secure computation, there's, we assume that some subset of the parties are malicious. Let's say that they're controlled by a polynomial time adversary. And we want to protect the honest inputs and outputs from this adversary. We want the adversary not to be able to learn anything about the outputs, and we don't want the adversary to be able to tamper with the outputs. And so security is formalized in these classical works by giving a simulator which does not have direct access to the honest parties and instead interacts with an ideal functionality. And we say that that a protocol is secure if there is such a simulator that can basically produce an outcome in the ideal world that's indistinguishable from the real world. Okay, so so like I said, the question that we want to ask is, can we achieve this definition of security in our model? So recall there are two efficiency requirements: limited local space for each machine or each party, and limited rounds. And so the question is, can we achieve security while respecting these requirements as much as possible? And so the first natural question is that everyone should ask probably is that, there's a large body of work on classical secure computation, and do any of these works apply in this model? And in general, the answer is unfortunately no, because essentially almost all previous work relies on a simultaneous broadcast round, where in this round, every party sends and receives messages from every other party. And this violates the space constraints for our protocol. And this is actually not surprising, because most of these previous works give general purpose compilers for any polynomial time functionality, and it's actually not known whether this massively parallel model captures all of P. So, however, there has been a recent line of work that started the study of secure computation in this model, starting with the work of Chan et al. In 2020. And this work shows that, in fact, you can take any insecure massively parallel protocol and transform it into a secure version with essentially minimal blow-up in the space and the rounds. And this compiler achieves security in the CRS model, and it also achieves what's called, it also works in the setting of honest majority, where we assume that like less than approximately 1/3 of the parties are corrupted. So there was a follow-up work by Fernando et al., which was able to provide a compiler that extends to the dishonest majority case, where we guarantee security even if there's only one honest party. But unfortunately, this protocol was only able to be proven secure in the much weaker semi-honest setting, where the assumption is that all parties follow the honest protocol specification exactly. So it's an important open question whether or not it's possible to achieve full malicious security for dishonest majority. And so to make a sort of a more complete picture, there's also an important definition of security that's in between these two definitions, and that's called semi-malicious security. And the assumption here is that all parties follow the honest specification, except that they're allowed to choose randomness maliciously. And the reason this is important is because it's been used as an important building block in many classical works in achieving full malicious security. So this is the state of the art prior to our work, and there are these important questions about whether we can achieve semi-malicious security or fully malicious security in the setting of all but one corruptions. And so with that, I'm going to state our results. So our first result is an impossibility. Specifically, where we show that it's impossible to get a general purpose compiler that achieves anything stronger than semi-honest security in the setting of all but one corruptions. And this impossibility result actually applies regardless of the trusted setup used. And our second result is a malicious secure compiler that works exactly in these two settings. And so the reason that we're able to do this is we first observe that our impossibility result does not imply does not apply to the programmable random oracle model. And so indeed, our compiler is given in this stronger model. And we're able to achieve the same efficiency properties as previous work, and the assumptions we rely on are succinct non-interactive arguments, indistinguishability obfuscation, fully homomorphic encryption, and the learning with errors assumption. Okay, so for the rest of the talk, I'm first going to give, I'm going to cover the impossibility result in a little bit more detail. And then after that, I'm going to give an overview of the techniques that we use to get malicious security. Okay, so first, the impossibility result. So this result is heavily inspired by the work of Hubacek and Wicks from 2014. And we're able to use the techniques and the ideas in their paper in order to make the following observation, which applies to any massively parallel protocol. So if you take any such protocol and you assume that this protocol provides either semi-malicious security or malicious security, then we show that it must be the case that the communication between the communication sent from the honest parties to the malicious parties is at least as large as the output. And in the most general case, that means that it could be at least as large as the input as well. And we're able to show this using very mild cryptographic assumptions. Okay, so let's think about what this implies in the case of all but one corruptions. So now we assume that only party one is honest, and let's try to analyze this party's communication complexity. So let's assume that there are Q rounds, and by the constraints of the model, we know that party one's total communication, or party one's communication in each round is bounded above by its space S. And then it follows that the total communication is across all rounds is Q times S, which again, by the limitations of the model, is much less than N. So this, of course, contradicts the lower bound on the communication, which I just described. So this is like the very high level outline of how we achieve our impossibility result. And I don't have time to really go into detail about how we show this lower bound, but I'll just say that the main idea that we use is we use the semi-malicious simulator in order to compress, to efficiently compress the output of a pseudorandom function, which contradicts security of the BRF. Okay, so now I'm going to talk about malicious security. And since the time is limited, I'm going to focus on a specific subcase of massively parallel protocols, namely those where the space, the size of the output is small enough that it can fit on the space of a single machine. And the reason I'm going to do this is so that we can talk about our techniques without without working in the random oracle model and having to deal with that. And at the very end, I'll talk briefly about how to extend to the general case. So our high-level strategy is the same as many other works. We're going to take a semi-malicious protocol and use some techniques and upgrade it to a malicious security. And it turns out that if we restrict ourselves to this small output case, the previous work contains a short output compiler that works for all but one corruptions, and it's pretty easy to show that this actually provides semi-malicious security in this setting. Okay, so let's first quickly talk about the most common strategy for getting malicious security starting with a semi-malicious protocol. So if you have a semi-malicious protocol, in classical secure computation, you can upgrade to malicious security by using zero knowledge. So in each round, you have every party prove in zero knowledge that it behaved honestly. So let's think about what happens when we try to use this kind of technique in our setting. So consider a protocol with the following communication pattern on the slide. And let's say that now party two wants to prove that it acted honestly to party one. So it's going to try to send a proof, and the proof is going to be with respect to some, public function called the next message function. And this function takes as input the private input and randomness of party 2, along with the transcript of the messages that party 2 has received so far. And it's going to output the message that party 2 is supposed to send to party 1. And so party 2 can send a proof with respect to this function that it acted honestly. But the problem is that if we get such a proof, this actually doesn't tell us very much at all, because it could be that the inputs to this function themselves are maliciously generated. So it could be that some of the preceding parties sent malicious messages. So what that means is that even if party 2 acted honestly, party 2's message could still be malicious. And so what we actually would want to prove in order to prove honest behavior for party 1 is we need to prove that party 2 generated their message honestly, and that all messages that party 2 received have also been honestly generated. So the reason why this isn't a problem in classical secure protocols is because in classical secure protocols, all parties broadcast zero-knowledge proofs of honest behavior every time they send a message. So by the time party 1 has received party 2's message, it's also received messages from all the preceding parties in all previous rounds, showing honest behavior for all of these preceding rounds. So of course, this won't work for us, because that means that party 1 has to receive order of the number of parties in communication just to verify a single message. And so that's like entirely too much communication for our model. Okay, so let's try something different. Let's imagine that party 2 has received proofs of honest behavior from all of its preceding parties. Now, what would be really nice is if party can sort of recursively compose their proof. So it'd be really nice if they can prove the following statement, like I generated my messages honestly, and I have proofs, I've seen proofs which prove honesty of the messages which I received. So if party 1 is convinced of this statement, then party 1 can be convinced of the honesty of the message. So it turns out there's a particular type of zero-knowledge argument which is very well attuned to this kind of recursive composition, and this is called a ZK snark. And the reason why is because, first of all, it's not interactive, which means the proofs can be recursively composed. Second is that it's succinct, which means the proofs don't blow up in size when being recursively composed. And finally, it's an argument of knowledge, which means that soundness of the proof is preserved under this recursive composition. But it turns out that there's still a problem with this approach, and that is that every time you recursively compose a snark, you end up with an exponential loss of security for each layer of recursive composition. So in general, it's fine to recursively compose a constant number of times, but anything much more than that, and you risk losing security of your argument system. So one of the main technical parts of our paper is devoted to solving this problem. And so I'm going to sort of sketch our solution here. So let's say that we've just finished a semi-malicious round of communication, computation and communication. And now each of the parties has a state which contains some secret state, as well as the messages received in this round, which we assume are public. So then after this, the parties are going to run a sub-protocol, which we designed and which we're going to call the commit and agree sub-protocol. And after this sub-protocol, every party is going to have a succinct commitment to to the states of every party, as well as openings for their particular state. In addition, all the parties will agree on this commitment. So the protocol guarantees agreement. And the tools that we use for this sub-protocol are standard cryptographic tools. So then once all the parties have these commitments to everyone's state, the parties are going to exchange openings. So what I mean by that is, let's say that party one sent a message to party two in the semi-malicious phase of the round. Then in this opening phase, party two is going to return an opening that shows that party two has recorded party one's message in some predetermined position J, which is fixed by the protocol. And so all parties exchange these openings for every message sent in the semi-malicious phase. So what that means is that now party one can prove honest behavior. So specifically, it can take its state, and it can also take the state from the previous round, which is presumably it saved. And then in addition, it can take the openings for all these messages that it sent in this round. And then it can compute a proof which proves both of the following points. First, that it did an honest computation. In other words, its state was updated honestly. And second, it communicated honestly. So it sent messages that it was supposed to the parties that it was supposed to, and these parties stored those messages honestly. So then we can have each party do this separately, and then we end up with m different proofs, and verifying the honesty of this round now reduces to just verifying the conjunction of the statements underlying these proofs. So now we can use recursive composition to aggregate all these proofs and produce a single succinct proof. And if we use a large array tree, we can achieve a constant depth, and which means that we only have to use recursive composition a constant number of times. Okay, so that's a high-level sketch of our ideas for short output protocols. So now let me quickly cover what we do in terms of long output protocols. So the high-level idea is essentially the same. So we're going to take a semi-malicious protocol, which we designed, which works for long output protocols. And this is in the random oracle model now. And I'll refer you to the paper for exactly how we do this. And so now what we want to do is we want to use the same techniques to compile this protocol to achieve malicious security. But there's a problem. So the problem is that since this semi-malicious protocol is now in the random oracle model, which so in general, if you want to compile a semi-malicious protocol in the random oracle model to a malicious one, you will have to prove statements involving random oracle queries. And in terms of snarks, this doesn't play well with snarks. There's no known snark that works in this setting. So the way that we end up solving this problem is we sort of carefully compile this semi-malicious protocol in sort of an ad hoc way that's specific to our protocol, and this allows us to achieve malicious security without ever proving statements involving random oracle queries, even though the underlying protocol does use the random oracle. And I'll refer you to the paper for this, for the details on this. Okay, so I'll just end by putting up a slide that restates our results. So that's all I have. Thank you.
Thanks a lot, Rex. If you have any questions, please come at the front. And also from Zoom, you can ask either, you can unmute yourself or paste your question on the chat. Okay. So Rex, can you say quickly what is the exact asymptotic overhead of your construction?
So I don't know the exact constants or anything, but in general, in terms of the security parameter and the input size, so we have a space blowup that's polynomial in the security parameter and independent of the input size, and the round blowup is just constant. It's a multiplicative constant. These are both multiplicative constant blowups.
Okay, thank you. So let's thank Rex again. Okay, so next we have Le Mans. I don't know if I pronounced this correctly. So Le Mans dynamic and fluid MPC for dishonest majority from Rahul Rashuri and Peter Shaw, and Peter is going to give the talk.
Okay, thanks for the introduction. So I'm going to talk about Le Mans, which is our new dynamic and fluid MPC protocol for the dishonest majority setting. This is joint work with Rahul Rashuri. So the slides not advancing. Sorry. Oh, is it advancing on here? Oh, I just can't see the laptop. Right. Okay, even if it's, maybe we can go back to this one.
Can you go here?
Yeah. No.
Why doesn't it go on the Zoom? Yeah, it doesn't go on the Zoom.
Okay, but I think the animations, okay, I just can't go back. Yeah. Okay, yeah, that's fine. I'll carry on anyway. Okay, so we're doing secure multi-party computation, where we have a set of parties with some private inputs, and they want to jointly evaluate some function across all their inputs. And in this case, we'll be considering the function to be an arithmetic circuit over the integers modulo p for some large prime p, and working in the dishonest majority setting, where possibly the majority of these parties may be maliciously corrupted under control of an adversary. Now, normally in MPC, the set of participants is fixed from the beginning of time. But in this case, we want to also allow potentially dynamic participants, so parties might drop out and rejoin later on during the protocol. So why might you want to do this? Well, firstly, allowing dynamic participants adds flexibility. So if the parties are doing a very long-running and complex computation lasting for hours or days, then they might not want to commit to being online and committing their resources for the entirety of the protocol, and they may need to drop out partway through. And a second possible motivation is actually for security. Because if the adversary cannot predict how parties are changing over time during the protocol, this may even make the protocol harder to attack and creates a moving target. And this is the case, for example, in the YOSO line of work for you only speak once MPC, but this is kind of taken to the limit, and that each party in the protocol only joins in to receive and send a single message before going offline. So the fluid MPC model is this work by Chowdhury et al. From Crypto 2020, which is what we build on in this paper. So in their model, they have the protocol divided into a series of time periods called epochs, where in each epoch, we have associated with that time period a fixed committee of parties who are running the protocol at that time. And they're the only ones to be online during that epoch. So outside of these epochs, we also have an input and output stage where the input providing and output receiving parties have to be involved, but those are treated separately. And the security assumption of the original fluid MPC work is that within any given epoch, that committee of parties always has to have an honest majority. So moving in a bit closer within the epoch, we have also two distinct phases. Firstly, a computation phase, where the current committee will do some local computation, potentially also interact with each other. And then secondly, a handoff phase, where they at this point have to know the identity of the next committee in the following epoch, and will reshare or pass on their state to the next committee by sending a single message to those parties before going offline. And depending on the number of rounds of interaction in the computation phase, this defines a property known as the fluidity of the protocol. And in the upstream case, where there is no interaction in the computation phase, the parties only do local computation before handing off their state to the next committee, this is called a maximally fluid protocol. So the work of Chowdhury et al. Presented a fluid MPC protocol in the honest majority setting with active security with a board. And their protocol could be maximally fluid, meaning that in each epoch, the parties only need to be online for one round of interaction to hand over their state. And also, importantly, to obtain an efficient protocol, you want this to have a small state complexity. So the size of the transfer from one committee to another is not too large. So in Le Mans, we want to build a similar kind of model for the dishonest majority setting, taking fluid MPC as our inspiration. But we have to change the model slightly to get something that works. And we're going to add a pre-processing phase ahead of time to the computation, where now we'll require that all the parties who might be involved at some point during the computation of the online phase have to be online in the pre-processing. But once that's done, then we move to the online phase, where parties can change and dynamically evolve across the different epochs, as in the fluid MPC work. So the only requirement is that in each epoch, you at some point will learn the identity of the parties in the next epoch before the end of that phase. And now for security, instead of an honest majority, we just require that each committee will have at least one honest party. So in this model, we present two main protocols, which can both be seen as variants of the speeds protocol for dishonest majority actively secured MPC, typically with static participants. And our first is a variant of speeds in the dynamic setting, where we don't quite have full fluidity. Instead, we restrict the online phase to always run within one single committee. But this might be a subset of the parties who took part in the pre-processing. And this is a more practical line of work and can essentially be seen as something that allows potential dropouts between the pre-processing and the online phase in speeds. The second protocol we call fluid speeds is more general and allows also the online participants to evolve by changing the committees across these epochs, as in fluid MPC. And both of these protocols are tied together by the pre-processing phase, which is the same in each protocol. And we have what we call a universal pre-processing among all of the participants, which also has a nice silent feature by building on recent advances in pseudorandom correlation generators. And the first protocol for dynamic speeds is also particularly nice because of the silent pre-processing, it actually has the lowest communication of any of the speeds-like protocols that were previously known, including ones just supporting static participants. So going a bit more into this pre-processing model, so the goal of pre-processing an MPC is just to output some correlated randomness to the parties that can be done ahead of time before they know the inputs to make the online phase of the computation run faster. And of course, the problem with this model is that generating this large quantity of correlated randomness is often very expensive, requires a large amount of communication amongst the parties. So silent preprocessing is a way of compressing this amount of preprocessing material to just some short correlated seeds, which can then later be randomly or locally expanded to produce a larger amount of correlated pseudo-randomness, like multiplication triples. And these can again be used in the online phase as before. And we do this building on advances in PCGs. So we want to build a silent preprocessing phase with this universal feature where we will run the protocol to generate preprocessing amongst the entire set of n parties, and then can later use this to generate preprocessing for any subset of size m on demand. And just to make this harder and more useful, I guess, we want to require that this is done without any interaction after the original preprocessing phase. So the main challenge here is that if you think about multiplication triples, for instance, then these are normally tied to a fixed set of parties, which you have to kind of know ahead of time. And while there are ways of resharing correlated randomness from one committee to another, these are usually interactive and require a large amount of communication. So as a warm-up, let me just take you through a simple passively secure example of how to do this for multiplication triples. So we want to generate beaver triples, which are these secret shared values ABC, where C is A times B. And each of these is additively shared across n parties, which you can think of as the entire set of preprocessing parties at this point. So rewriting the product A times B here as a summation of pairwise products AI times BJ, then we get this sum of n squared of these pairwise products. And notice that if we want to instead generate a triple in, say, a subset of, say, half of the parties, then we just need to restrict this summation up to n over 2 instead of up to n. And then it suffices to if we have these sharings of pairwise terms, we can just take the ones we need to compute a triple in any subset of the original n parties. So we'll start by distributing shares of all of these pairwise products among the parties. And this allows us to then extract one multiplication triple from each of these sets of sharings in any chosen subset we like dynamically in the online phase of the computation. And to do this silently and with low communication, we'll be using PCGs. And note that because each of these products is just involving two secret shares, so AI and BJ, we only need a two-party PCG to generate this sharing. And thankfully, this can be done quite efficiently using a variant of the LPN assumption, and allows us to translate this preprocessing to have a silent implementation. So a few things we have to take care of when actually making this work, like making sure that these AI and BJ terms are consistent across different sharings. But thankfully, with small tweaks to the underlying PCGs, you can make this work. OK, so that's the passively secure setting. Now, if we want active security, we don't just want Beaver triples. We usually use authenticated triples, like in the speeds protocol, where each of these values ABC is now multiplied with a random secret MAC key delta, and again, secret shared to the parties. So this introduces an extra challenge. Because now if you look at the product delta times C here, and this is going to be a degree 3 term in all of these secret values, delta, A, and B. So if we try to apply the same trick by decomposing the sum into all of the cross products, then we've now got n cubed of these terms, delta I times AJ times BK for every of these index. And this is quickly getting really expensive as the number of parties increases, so isn't so practical. So instead, we just take, I guess, the most obvious solution, which is just to forget about this last term of the authenticated multiplication triple and see if we can make the online phase of the speeds protocol work without this. So we'll have this universal preprocessing, which now puts partially authenticated triples without the last term, where we use this passively secure degree 2 approach from the previous slide to generate all the other terms. So putting this together, the dynamic preprocessing protocol looks something, or dynamic speeds protocol looks a bit like this. So the preprocessing phase will sample these random sharings, A and B, and then distribute all of these secret shares of pairwise products for the cross terms. And then in the online phase, when we've decided on a committee who wants to use some of this preprocessing material, they can locally extract the right shares to obtain this partial authenticated triple, just missing the MAC on the C term. And with a small amount of interaction, they can do some fairly lightweight computation to add the MAC to the C value. And then we'll evaluate the circuit as usual and run some consistency check at the end of the protocol. And this consistency check is necessary because we've now actually added this MAC to the online phase instead of doing it in the preprocessing in a verifiable way. So we have to add an extra check to make sure that this is done correctly. And for this, we use this randomized circuit evaluation procedure from the work of Chowdhury et al. And so this online phase has got a little more work than the standard speeds protocol because of the check and the extra authentication of C. So it's around 3 times more communication than previous protocols. But for this cost, we do get this dynamic feature supporting dropouts after the preprocessing phase, as well as this silent preprocessing with very low communication. OK, so that was dynamic speeds. And in fluid speeds, we want to additionally support changing committees in the online phase. So here there's a few more challenges we have to take care of. The first of these is the requirement that we want a small state complexity when transferring the state from one committee to another. Because the way these the speeds online protocol and the dynamic online protocol works is to have some verification checks at the end of the protocol, which are like batched for the entire circuit. And that kind of inherently requires storing the entire state until the end of the protocol, which wouldn't work in this fluid setting. So instead, we propose incremental variants of the MAC check used in speeds and this circuit verification procedure to allow this to be done kind of on the fly without blowing up the memory complexity for the fluid setting. And the second challenge we have is that because of the nature of the way the universal preprocessing works, is that when you have two different committees getting a multiplication triple in the online phase, then they will end up with triples authenticated under different MAC keys. So we have an inconsistency between the MAC keys that are used from one committee to the next. It means at some point, this is going to break when you try to combine the computations from those committees. So to fix this, we have to add an extra protocol to allow switching the MAC key from one committee to another. And putting these things together in a fairly careful way, we can actually obtain a maximally fluid multiplication protocol using this preprocessing, where each committee in any of the epochs only needs to be online for a single round of interaction. Okay, so I'm not going to go into the details of most of this, but let me just say a little bit about this MAC key switching protocol, which we use. So recall that the goal is to transfer a MAC of some secret shared value X from one committee to another, where the starting committee on the left will have it authenticated under, say, a MAC key delta A, and the goal is to transfer this to the right committee under their key, which are called delta B. And if you look at this problem, it might seem kind of impossible to do if we just want to do a single round of interaction from left to right to allow the first committee to go immediately offline. Because this committee doesn't know anything about delta B, how can they possibly get the right shares to that committee? But we have a trick up our sleeve, which of course is this nice universal preprocessing protocol. And by taking advantage of that in the right way, we can make this work. So from the preprocessing, the parties have shares of their MAC keys. And we will also use a variant of this where we can get shares of a random value R shared amongst the left committee, together with a MAC on this value, but now under the MAC key held by the right committee. The MAC here is not actually exactly a speeds MAC, it's slightly different. It uses pairwise MACs. But using a similar trick to generating the authenticated triples, you can generate this kind of random MAC value. And once you have this in the online phase, it's quite easy to transfer X from one MAC key to the other by essentially first resharing the shares of X to the next committee, and then opening X plus R as a mask, and some special correction values for the MACs, which allows the committee on the right-hand side to get the correct sharings. So there's a few details hidden under the rug there, but that's the rough idea of what this gets you and how it works. And that's all I'll say about the technical side. I'll just end with a little bit on the concrete or asymptotic even efficiency of this. So the baseline we look at is the classic speeds protocol with one of its variants of preprocessing based on homomorphic encryption, where the main communication cost in the online phase is around 2 field elements per party per multiplication gate, while the preprocessing scales linearly with both the number of parties and the circuit size. And our dynamic speeds protocol vastly reduces the cost of the preprocessing to be only logarithmic in the size of the circuit by using these PCGs. And because the price we pay is this 3 times extra online cost because of the extra work we have to do there. The fluid protocol is a bit less efficient. The constants depend largely on the fluidity which you want to achieve. But it is, at least in the amortized sense, a constant per multiplication gate. And the preprocessing is the same as in dynamic speeds because yeah, they're identical. Okay, so that's all I want to say. I'll just leave this slide up here as a quick recap of our main results. And if you want to see more, you can check out our paper on ePrint. Thanks for listening.
Thank you very much for a very interesting talk. So in the offline phase, you didn't generate the MAC of the C. Instead, you do it on the online phase. I wonder whether it can be pushed back to the offline phase, or it's just a matter of saying sublinear communication code.
So if you're happy to allow a linear amount of interaction in the offline phase, you can do that. But I don't know how to do that efficiently, like whilst retaining the sublinear property in the preprocessing.
I see. But in general, it doesn't that make more sense, like push as much as communication codes in the offline?
Yeah,
phase?
so I guess we push kind of part of the heavy computation work for doing that authentication of C. So the part that's in the online phase, it's some extra communication, but it's at least, it doesn't have any heavy crypto on it. So it's lightweight in that sense.
I see.
So I think it depends on the application, whether you want to keep that in the online phase or push it to the offline.
I see, makes sense. Thank you.
So first, thank you for the nice talk. And then I
Thanks.
have a sort of a speculative question. You know, having this requirement that all the parties be there initially, you know, of course, it'd be nice to alleviate that. And I'm curious whether you think it's more promising to sort of throw out authenticated triples altogether and pursue some other approach, or whether you might be able to use the PCGs online as new parties enter that have never been seen before.
Yeah, so it's a tricky one. I mean, the problem is with these pre-processing protocols, they're kind of designed to generate a very large batch of multiplication triples, right? So if you generate that like more online on the fly, then that committee is going to use all of them.
Sure.
And maybe a more promising approach might be to try to design a PCG where you can like reshare the seeds from one committee to another in some efficient way.
Yeah.
But so far, it doesn't look easy.
Cool. Thank you.
Oh, yeah. Thank you. Thank you very much for the talk. It was a great talk. I just wanted to ask, what do you think are the big open questions in this kind of like fluid MPC area? And like, how far is it from being used in practice, right? Because like the first use that comes to my mind is like kind of blockchain MPC stuff where the users are not always assumed to be present. Like, how far are we from like being able to actually like implement and use this?
Yeah, I think it's a really interesting question. I think there's a bunch of trade-offs. Like, so in the fluid MPC line of work, one thing we sacrifice, at least in the honest majority setting, and to an extent it's inherent in dishonest majority, is getting guaranteed output delivery or preventing malicious parties being able to abort without any penalty. So in the YOSO work, with the honest majority, they get guaranteed output delivery, which I think is very desirable in the blockchain setting, but their protocol is also very impractical. So there's definitely room for improvement with making that practical, or perhaps making this dynamic fluid MPC dishonest majority setting more robust in some sense, maybe identifiable abort or something.
Yeah, thank you very much. Sounds good.
Thanks.
I had one more question. I'm sorry. So can you go back in the table? So the cost is linear, right? In the online phase, it's not constant. Can you go back to your table? What do you mean here with?
So this is the cost
What did you
linear in the
say?
circuit size, you mean?
Yeah. So it should be linear, right? In the
Yeah,
number of parties.
Yeah.
Okay. And what happens, for example, if you have fluidity 2, like how the constants are changing?
What happens with what, sorry?
If you increase the fluidity, let's say you increase to 2.
So I think 2 would maybe it would save you a little bit. I think we estimated that once you increase it to like 3 or 4, then the online cost would actually get very close to the dynamic speeds cost. Because there's a lot you pay just to get that maximal fluidity.
Okay, got it. Are there more questions? Let me check quickly the Zoom chat. Yeah.
So this is per party, right?
Yep.
So in your protocol, don't you do this everyone talks to everyone kind of thing?
Yeah. So it's n squared because you count per party.
So the online is per no.
Oh, and the online you don't have to talk to everyone.
Okay.
It's like in speeds you have the king trick, where you send to one party and then they send to the rest. You can you can kind of amortize with that kind of stuff.
Okay, I see. Thank you.
Okay, let's thank all the speakers of the session and Peter again.